Good morning everyone, I'm Mr. Ish. I have laid the conceptual framework for determining or the process by which we should look at volumes of curves. You know, when you have the curve and you give it a dynamic movement, you bring in the volume dimension into that picture. In this video we'll be looking at examples, specific examples, integral examples, and we will see how we can go about determining volumes of curves. Again, I want to start here with a very quick, you can say a brief introduction. Here we have two types of solids we're looking at. We have rotational solids and we have revolutionary solids. Look over here at this part A, rotational solids, and part B, revolutionary solids. Now some textbooks will call all of these things a single label of solids of revolution. I like to make the distinction between the two types. In a rotational solid, when you have a curve and you give it the dynamic movement, there's a specific point on that curve which will never move out of place and it will stay on top of the line of axis. If you take this curve which looks like a root x, y equals root x, and you give it a rotation around the x-axis, you have this little apex of this solid which forms, which always remains on point. As the object rotates, it remains on point. Hence I call it a rotational solid because it's undergoing a true rotation. And if you were to take a cross-section of this solid, you would have a disk come into place. And you know, a disk can easily give rise to a radius, and you can calculate the area and take it through integration across your interval. And then again for a rotational solid, if you look at this other example, the same function graph, root x, it could be anything but it looks like a root x to me, but now you make the rotational axis y-axis. Here it was a horizontal line of axis, but here's a vertical line of axis. Now you rotate this around this vertical line, you'll still have a specific point, this point right over here, which corresponds to this point right over here, which stays on point, and you have the line of axis going right through it. Line of axis right to this point, and that point will stay fixed as the object rotates around that line of axis. Again, this is a rotational solid, but if you take a horizontal cross section, you end up getting a washer, not a disk but a washer. But again, for a washer, you can have an inner radius right up to this point right over here, and you can have an outer radius developed right up to this point, outer radius, and you can have an inner radius, and outer radius gives rise to outer area, inner radius gives rise to inner area. Again, the most difficult part of these type of questions is the determination of radius, and you can only do that if you picturize your question so you can orient yourself towards that radius determination. Now look here at B, revolutionary solids. In a revolutionary solids, you won't have rotational movement, even though from a broad perspective it is still a rotation about some sort of a fixed line, except here the rotation is a true revolution because there's no point, none of these points at the apex or at the other end are staying fixed in their position as it moves around that line of axis. All of these undergo a translatory movement, a circular translatory movement. Look, here's the same point here, here's the same point here, here's the same point here, but they'll all undergo a complete and true translation as you go around this horizontal line of axis, and here the line of axis is x-axis, and we have a solid of revolution or a revolutionary solid, kind of like a planet moving around the sun. And you can see how three-dimensionally this solid would look, and this solid right here and this solid here. But if you take a vertical cross section over here, you end up having a washer. So almost exclusively true revolutionary solids will give rise to washer cross sections. Rotational solids can give rise to both disks and washers. And again here you can do from the center of this washer, if you draw a line and then you look over here to this first part, you have your inner radius. If you just do another line and you look here up to your top item, you have your outer radius, your top marking over here. So inner radius will give rise to inner area, outer radius will give rise to outer area. And you know we have to worry about areas over here because when you're doing volume determinations, we're always looking at some sort of interval, and then we're looking at the integration of that area which develops but across that integration interval, and we end up giving rise to a volume. And the only reason why a volume comes about from an area is because of the movement dynamic that we're looking at, and the movement here can be a rotation or revolution along some line of axis. So as you look at the questions in this video, keep this in mind. For those questions where we will have a horizontal line of axis, and you know what that is, a line of axis in a horizontal x dimension, and we're going to rotate about it like this, we're going to rotate around it, we're going to be looking at our equation in the forms always y equals format, and we will do integration with respect to dx. So our equation eventually will come out something like this. You can have pi before the integral or after integral, it doesn't matter, but for consistency's sake let's keep it always out of the integral sign while we remember to do so. So volume will always equal to pi, and our interval, whatever it will be, we'll have our area equation in the form y equals. Remember, a of x is in the y equals because a of x is synonymous with saying f of x, right? Which is also synonymous with saying y. But integration with respect to dx. You have to keep this nuance in mind. For any question that will arise in this video, and we have a vertical line of axis, something which is along a y dimension, and then we're rotating about that, you will now present your equations, and all of these questions that will be presented, you will easily be able to express either y equals or x equals. There won't be any issue with regards to that. And then you'll do with regards to dy, and your volume presentation will be, it could be any interval over here. It would be a, but with regards to y, dy, just like how you were looking at the area under the curves. So here's our question. The area bounded by those curves, y equals x cubed, y equals 8, and x equals 0. When you're looking at x equals 0, that's your y-axis line. When you're looking at y equals 8, you know that represents a horizontal line going across right over here, y equals 8. And you know what the cubic function x cubed looks like. It's not a difficult graph. It would normally continue down here, but since we're not looking at that quadrant, because these areas bind it to here, the first quadrant, in terms of just the area which we're looking at, the area between the curves, which will then transform into a volume, we're looking at that. The rotational axis is a vertical one. When you do your volume, your rotational solid, because it is indeed a rotational solid, because it's this point right here will always stay fixed like a spinning top's apex around which it rotates. You have a solid which will develop, and it will look something like this, oriented in a vertical direction but having a vertical line of axis. A slice through here will always look like a disc. A through and through solid, it will look like a horizontally oriented disc. That's just my radius line. You don't have to draw the radius line, but that's exactly what it is. A vertical line of axis. Equations must be presented of your curve in the x equals format, and you must integrate with respect to dy, and you must determine an interval along a vertical dimension. What can our interval be? This right here gives us our clue to our interval. We're going from 0 all the way up to 8. So that's my interval, 0 to 8. The vertical extent of this region between the curves is 0 to 8. Let's convert this. Y equals x cubed becomes x equals cube root y. And our radius determination is always from the line of axis, which is here my y-axis, up to the outer edge. Right here to right here. And the radius here is exactly your function. But your function has been converted into the appropriate format. So radius here is equal to y to the 1 over 3. Area must equal to pi r squared, which is pi y to the 2 over 3. Then volume must be determined using your integration technique from the lower limit 0 up to the upper limit 8, y to the 2 over 3 and dy. You know you have to do the polynomial technique here. N plus 1 divided by n plus 1, which is not hard. When you integrate it, you get y to the 5 over 3 divided by 5 over 3 from 0 in the bottom lower limit to 8 upper limit. And then you get 3 over 5 pi times y to the 5 over 3, 8 and 0. You have to run this 8 through this value of y and subtract from that 0. 0 is meaningless, but 8 to the 5 over 3 is not too hard. Think of your laws of exponents. 8 is really 2 cubed, and then you're doing that 5 to the power 5 over 3. These cancel out. What you end up with is 32. 8 to the 5 over 3 power 5 over 3 is equal to 32. 32 times 3 is equal to 96. 96 times pi over 5 is 96 pi over 5, and this represents the volume of this rotational solid. My technique here is not bad. We don't have a silly mistake because 8 to the 5 over 3 is indeed 32. 32 times 3 over 5 will give you 96 over 5, and then there's a pi. And we're done. Not a difficult question. Good question. Okay, let's look at this next one. Y equals x, the area bounded by these two curves, which will go to the volume determination. Y equals x squared, and our dynamic movement or rotation is around the x-axis. Equations must be presented in the y equals format, and you will integrate with respect to dx. Always start with a graph because that will help orient you towards the problem. Y equals x looks something like this. Y equals x squared looks something like that. And the area between, or the region between the curves, is over here. How do you know what the interval is? It's easy. you do x equals x squared, the two graphs, you have to find the intersection points. X minus x squared is equal to 0. X isolate into 1 minus x is equal to 0. Solve for x and you'll get 0 comma 1 and that'll give you your interval. Not hard. If you rotate this around the x-axis, which is what it is, you end up having a rotational solid, but it will have a washer cross section. Here's my x, here's my x squared, here's my x, and here's my x squared, but in the mirror image. We're looking at the area between these two curves, but then we take it through the rotational movement. It brings a volume into the picture, and we have a solid which will look something like this. And you know it has that type of a appearance with this inner part being empty but closed at the end. It's a rotational solid because this point right over here, which corresponds to this point right over here, will always stay fixed about that line of axis. But when you do a vertical cross section slice, you end up seeing a washer come into place because you have this open area in between, which is abutted against these convexities of this x squared graph. Anyhow, you do have a washer in the picture, and therefore you must have an inner radius and you must have an outer radius. You have to determine, but it's not hard. The inner radius is from your line of axis, which happens to be your x-axis, up to the first curve right here, and then the outer radius is again from the line of axis but to the second curve. So the inner radius and everything here is in the proper format in terms of y equals format. Inner radius is from your x-axis, which is really 0, but 0 is meaningless. You don't have to write 0 plus, but I'll just do it for the sake of the video. 0 plus the first curve is x squared, your first inner radius. Your outer radius is 0, which is your x-axis, but to the next curve, which is x. Then you must have an inner area and you must have an outer area. The inner area is basically x squared squared, which is pi x to the 4. The outer area is this radius, the outer radius squared, which is pi x squared. Then volume is not hard. You send this to the formula, outer area minus inner area integrating through that. So volume is equal to pi. You have your interval 0 to 1. We've determined that by the intersection points 0, 0, 1, 1. Outer area minus inner area with regards to dx. Integrate this. You'll have pi. You'll have x cubed over 3 minus x to the 5 over 5, 1 and 0. When you do this, you're essentially looking at 1 over 3 minus 1 over 5. Because the zeros are meaningless, 1 over 3 minus 1 over 5. You'll get 2 over 15. But you can rewrite it again as 2 pi over 15 as being the volume of this rotational solid, which has a cross-sectional appearance or slices of washers. Of course, here at the very termination or the terminus of the solid, you won't have a washer, you'll probably have a disk, because eventually it'll close out over there. This region of empty space, which is bounded here by this convex portion of the curve, which is the x square, right? It doesn't go through and through as an empty space all the way through. It closes eventually at the end. But this area from here to right over here will always be your empty space, giving rise to the washer parts, or you can call these donut rings, but giving rise to the inner part of this washer, the open part of the washer. But the volume is good, 2 pi over 15. In the last two examples, we look at the same two curves from the previous question directly preceding this, but we'll look at a different line of axis. We have y equals 2, which is a horizontal line of axis. So again, equations have to be presented in the y equals format, and we integrate with respect to dx. And we have again the interval, because the same equation, the same intersection points, therefore the same interval in play. Start here with the graph. Y equals x. Y equals x squared, and the region between the curves is right over here. So this intersection point is 1, 1, but our rotational line is a ways away. Y equals 2. And we're revolving or rotating around this line. You're going to have a revolutionary solid develop because of the empty space which will be in between. There will be no fixed point that will stay firmly in place during the movement. It will always be circulating in a circular orbit. There will be a true translation in effect. Therefore, we'll be dealing here with a revolutionary solid. And then we have to deal with inner and outer radii. So what does this look like in terms of a solid? Well, here's my functions right here, x and x squared, my line of movement, and then I'll have a similar presentation come from here on the top, and we have rotation or revolution around this y equals 2 line. You'll have a solid which will look something like this. I'm not going to draw it too perfectly because this will be one of those difficult ones to show. Kind of like an open ball This entire space here between is going to be an open bowl with a smaller opening here and a larger opening here in the back. And if you take a vertical slice, you will obviously be dealing with a washer over here. Therefore, you'll have inner and outer radii to deal with. What's our inner outer radii going to be? Always from your line of axis. Line of axis here is horizontal. Equation in the y equals format and with respect to dx. Let's look at the inner radius. The inner radius is going to be from the line to your first curve. That's your inner radius. From the line of axis to the first curve, what am I seeing? I'm going in the opposite direction here. I'm going downwards. If from here, line of axis to here is 2, and we know from here to any of these curves is your functions x squared and x, then the difference of those must give you your radius. And your inner radius will be 2 minus x. Because the total length over here is 2, and then from here to this first curve which you see coming from up down, from this line downwards, the first curve is x, then it must be 2 minus x, because the distance from your x-axis to that curve was in x. Therefore, distance from y equals 2 to that curve must be 2 minus x. And likewise, similar analogy and logic gives you 2 minus x squared for your outer radius from this line up to this next curve right here. It's 2 minus x squared. And then you know inner area here is going to be a polynomial. You do square of this and pi r square always, right? You'll have a 4 minus 4x plus x squared and pi, right? Outer area, inner area, outer area, it doesn't matter how you present them out. Just make sure you don't confuse yourself with the terminology here. It'll be 4 minus 4x squared plus x to the 4 pi, and then volume is always equal to outer minus inner. Bring the pi, bring the 0, bring the 1. Your interval, your outer area, 4 minus 4x squared plus x to the 4th minus your inner. The 4's will cancel out because as you open up the parentheses, this 4 and that 4 will cancel out. Minus 4x plus x squared, and with regards to dx, if you open it up, let's see what happens. You have 0, 1, the 4's cancel out. You have a minus 4x squared, which will hit with this minus x squared, will become a minus 5x squared. This right here is just basic algebra, you can do it on your own. X to the 4th will stay as x to the 4th. Minus will become a plus 4x and dx. You can integrate this very easily and come up with a good answer. I won't take this through the integration process because you know you have to do n plus 1, n plus 1, n plus 1. Then you have to integrate over 1 and 0. All of that is polynomial integration, direct integration, which you should know how to do. And let's just write a volume over here. Well, let me go against what I'm saying and let me at least take it to the next step. Minus 5x cubed over 3 plus x to the 5 over 5 plus 4x squared over 2, which can be simplified to 2x squared. And from 1 and 0. Now if you integrate this, you'll get a good answer over here, and that good answer will be 8 pi over 15. And that'll be the volume of this solid. And this right here is a revolutionary solid because again there's no fixed point around the line of axis that is staying firmly in place. Everything is undergoing a translation, a translatory circular movement. It's a revolutionary solid. So we end our video with this last question. Here's our question: y equals x squared. Similar function as before. The preceding two examples have had the same, except here we've changed our line of axis. Our line of axis represents a movement around a vertical line, x equals minus 1. When you know we have a vertical line of movement, we have to present equations in the form x equals. And we have to do integration with respect to dy. And we have to have limits along a vertical dimension. You know for these two equations, the intersection points are 0, 0 and 1, 1. Well, you already have presented there your intervals along the x-axis and your intervals along the y-axis. It's 0, 1 or it's 0, 1. In terms of horizontal limits or vertical limits, so everything is already provided. Start here with the graph and x squared, and we're doing a movement along this line, x equals minus 1. You know you're going to have a revolutionary solid develop over here about this axis line. Let's look at it, what the solid would look like. We have something over here on this side which looks like that. Then we have our x equals minus 1, then a little distance away, equal distance away, we have this corresponding mirror image develop, and then we have a bowl-like shape volume develop, which will be open through and through, because you know you have all of this open space from right over here to right over here, where the other then portion of the curve builds up. This entire area is open. It's smaller opening here and a larger opening here on the top. because these curves are divergent. A horizontal slice will give you a donut-shaped ring, or as we call it in textbooks, a washer. A washer cross-section having three-dimensional features, which will have inner and outer radii measured always from your line of axis, which is x equals -1. Your inner radius to this first part and your outer radius to this other part right over here. What's our inner radius is? Remember, dimensions have to be positive. Just because this x equals -1, it's still 1 unit away from this x equals 0, your y-axis. It's still 1 unit away. Not -1 unit away, but positive 1 unit away. The first curve you hit when you're going for your inner radius is this, y equals x or x equals y. Therefore, your inner radius is 1 plus y. Remember, equations in the x equals format. Your area inner will be pi r square 1 plus y square pi, not hard. Outer radius will be measured from that line of axis, which is x equals -1, but to the next curve which you hit. The next curve you hit is actually x squared, but you have to look at it in root y form because it's in the x equals format. So here again it's 1 unit away from the x equals 0 line, but then it's root y units away to the actual curve, so it's 1 plus root y. And the area outer will be 1 plus root y square pi. Integrate outer area minus inner area over your interval 0 and 1. Volume is equal to, isolate your pi, bring it out. You'll have outer area 1 plus root y. You'll do this polynomial expansion, which is not hard, minus 1 plus y dy. When you expand this polynomial, you'll get a certain expression. You'll expand this, you get a certain expression. The ones will cancel out. Let's expand it out a little bit here. 1 plus 2 root y plus y minus 1 plus 2y plus y square. The ones will cancel out. You'll end up having an expression which will be volume is equal to pi from 0 to 1, right? 0 to 1. You have a 2 root y plus y, and this minus 2y is a minus y, and this minus y square with regards to dy. When you integrate it, you open it up, you'll have 2y to the 3 over 2 over 3 over 2. You can flip this around, you'll get 4 over 3 minus y square over 2 minus y cube over 3 from 1 to 0. You're basically looking at just this towards your final computation. You're looking at a 4 over 3 minus 1 over 2 minus 1 over 3. You can do a common denominator of 6, and when you simplify it all, you'll get a good answer. Let's do a common denominator. 6, 3 goes in 6 2 times, you have 8. 2 goes in 6 3 times, 3. 3 goes in 6 2 times, 2. So 8 minus 3 minus 2 is 8 minus 5, which is a 3 pi over 6. 3 pi over 6 divided by 6 gives you a pi over 2 as being the volume of the solid. So let's just put right over here, the volume over there for this revolutionary solid ended up being pi over 2. You can get a numerical value, just take pi 3.14, whatever it is, divided by 2, and that'll give you the volume of this revolutionary solid. Every single bit of this object or the curve, the region between the curves is moving in a translation. There's no rotation, true rotation. It's a true revolutionary solid. Everything stems here from a good graph and a determination of whether it's a horizontal or vertical line of axis, because that clues you into the type of integral equation format that you will have. So that's it for this video. Thank you for watching. Have a nice day.